Okay, I'm going to take a look at problem 7.29. In this problem, you have a shower head that's where water's coming in through a shower, and you have a shower drain that's partially clogged. Okay, so what you're going to find in this problem is that the water essentially is coming in quicker than it can drain, and after some period of time, this will fill the bottom of the shower. Okay, so that's basically what we're looking for, is to see how much time goes by before the bottom of the shower will begin to overflow. Okay, so we're looking for this time t. I said delta t, so basically from the time essentially, we start, the shower comes on till the time it starts to overflow. That represents delta t. Okay, so what I define is the diameter in, this is the shower head diameter, the velocity of the water coming in, and here's the mass flow rate. I use this as a mass flow rate out. Okay, so this is out going through the drain. Okay, so we're given some information here in terms of how the water's coming in to the shower and how water's leaving it. Okay, the last thing I did here was just come up with the volume for the shower. So this was the information that was given, and I just converted over inches to feet, which was 4 inches. So here's the volume of the shower. The way I defined it here, I defined it as like a delta VS, so meaning like the change in volume, which is essentially from being empty to when it's actually full. Okay, that's my delta VS. All right, governing equations. The way I approached it was volume flow rate. You'll see the publisher's solution did a little bit. They did a mass flow rate. To solve it, I did it with volume flow rate. Okay, so here's some governing equations. Here's our cross-sectional area times our velocity equals our volume flow rate. Cross-sectional area of a cylinder, or a circle, that is. And here is volume flow rate defined, right? It's just change in volume over respect to delta V over delta T. It's constant, so we can write it in this form. All right? Okay. So in terms of the volume flow rate, how is it flowing out? It's just going to be whatever's coming in minus whatever volume flow rate. I called this delta VS, which is what's filling the shower tub, right? Okay. And the last one is just mass flow rate. How does mass flow rate relate to volume flow rate? It's just the density times the volume flow rate. All right, so I found these, just thinking about it, that these could be useful equations, right? You may or may not have written all these down at this point, okay? But some of the important ones, so like this is important, and this one it's important to start with. And then how is this related? It's related by this, okay? Okay, so first part I did was take a look at coming up with, I'm trying to essentially solve this equation, okay? And I want to come up with the volume flow rate of how quickly it's filling the shower, essentially, okay? And then I know that if I know the volume and I know how quickly it's filling the shower, I can essentially use this relationship here, right? Okay, or this equation here. Okay, so dot Vn, here's my volume flow rate, is the cross-sectional area in of the shower head times the velocity in. Okay, well, I kept this this is in inches. Here's the radius of that shower head, and here's the velocity. So I just square the radius times pi gives me the cross-sectional area, times this gives me my volume flow rate. All right. I originally did it. I made a small error here, but I corrected it. So it comes out to be 63.6 inches cubed per second. All right. Well, I need to change that over to feet cubed per second. So I made the conversion here, which is 1 foot is 1728 inches cubed, right? Which would just be 1 over 12 times 1 over 12 times 1 over 12, right? Okay, so that comes up 3.68 times 10 to the minus 2 feet cubed per second. So the second part of the problem, I'm looking for the volume flow rate out, okay, which is essentially what's going down the drain, right? So I can use the relationship of mass flow rate out times the density of water gives me, I'm sorry, that mass flow, volume flow rate times the density of water gives me mass flow rate, right? Well, I'm looking for the volume flow rate, so then I just divide the mass flow rate by the density, and I can come up with that since mass flow rate's given, and this can be looked up, right? So the mass flow rate was 0.03 slugs per second, and then you can look this up. It comes in it's 1.940 slugs per foot cubed. Perform the calculation, you come at 1.55 times 10 to the minus 2 feet cubed per second. So this is the volume flow rate out. Okay. So now we have enough information to actually go and solve for delta T. Okay. And the way I did it was that original equation we had, the volume flow rate out equals volume flow rate in minus the volume flow rate filling. Essentially, I'm using this to mean filling the shower, right? The tub. Okay. So the dot flow rate, volume flow rate out minus the volume flow rate in equals, I just rearranged this equation, and then I multiply both sides times minus 1. So this side of the equation times minus 1, this side times minus 1. And then I just took this and substitute in for with delta Vs over delta T. Okay? So that's really this is the rate at which the shower is filling, right? The base of the shower is filling. Okay. So then I just rearrange this equation, divide both sides by this, and then multiply both sides times this, and then I come up with delta T by itself. Then I have the change in volume, which is essentially just the volume of the shower, because it was empty initially. And then divided by the volume flow rate in minus the volume flow rate out. And when you do that, this is times 10 to the minus 2. Kind of messed it up here. Did it in pen, right? I should have done it in pencil, but I didn't do that. So 3.68 times 10 to the minus 2 feet cubed per second. This is the rate at which it's coming in, which is greater than the rate at which it's leaving, so we know it's going to fill. Minus 1.55 times 10 to the minus 2 feet cubed per second. And then that's, you divide 2.08 feet cubed divided by this, what you found in that. And then that comes out to be 98 seconds. And that is it. Okay. And you could check the author's solution. It's I left that in the solutions area, so you can look and compare and see the way that the author did it or the publisher did it. Okay, so that's it for that one.